Welcome to day 8 of our Principles of Programming Languages course. Today we will be exploring the concept of type safety and type checking. In this session, I will guide you through these important topics that ensure our programs run reliably and safely. Let's begin by defining what we mean by type safety. Type safety refers to ensuring that operations in a program are performed on compatible data types. In simpler terms, it prevents errors caused by mismatched data types, enhancing the robustness and reliability of the code. This is a crucial feature in many programming languages as it helps reduce runtime errors and maintain program correctness. Type safety is not just a theoretical concept, it's a practical necessity in modern programming. Some languages like Java and Python ensure a degree of type safety by enforcing rules about how types interact. Other languages like Haskell are known for their strong type systems which help prevent a wide range of bugs. Next, let's explore the difference between compile time and runtime type checking. In compile time checking, the compiler verifies that types are correct before the program runs. This helps check errors early in the development process. On the other hand, runtime type checking happens when the program is running. Errors are caught only when an operation is attempted on incompatible types. This type of checking allows for more flexibility as seen in dynamically typed languages like Python and JavaScript. However, it can lead to errors that are only detected when the code is executed, making debugging more challenging. Let's look at an example of type errors. In C++, if you try to assign a string value to an integer variable, the compiler will flag it as an error during the compilation process. For instance, declaring an integer and assigning it a string will result in a compilation error because the types are incompatible. In Python, this kind of error can occur at runtime. If you try to add a string to an integer, Python will throw a runtime error saying the operands are of incompatible types. These kinds of errors are harder to catch compared to compile time errors because they only show up during execution. Now let's talk about static versus dynamic type checking. Static type checking occurs at compile time, ensuring that type-related errors are caught before the program runs. In statically typed languages like C++ or Java, the compiler checks for type correctness during compilation, helping to prevent type mismatches. Dynamic type checking, however, happens during the program's execution. In dynamically typed languages such as Python or Java, you can change the type of a variable during runtime and the language will not enforce type checking until the operation is performed. This provides more flexibility but can result in runtime errors if types are mismatched. Type inference is another interesting feature that helps ensure type safety. It's the ability of a programming language to automatically deduce the type of a variable without needing explicit type annotations. For example, in C++, you can use the auto keyword and the compiler will infer the type of the variable based on its assigned values. In Python, the type is inferred at runtime. If you assign an integer to a variable, Python infers it as an integer. Later, if you assign a string to the same variable, it infers the type as a string. While this makes the code more flexible, it also requires careful attention to avoid type-related issues. There are several mechanisms to maintain type safety in programming languages. One of the most common is type annotations. Type annotations allow you to explicitly define the data types of variables or functions or function parameters. In Python, for example, you can annotate the types of function arguments to make the code easier to understand and debug. Another mechanism is strict type mode, which enforces the use of specific types. TypeScript is an example of a language that enforces strict typing, helping prevent issues that arise from dynamically typed languages. Additionally, some languages use runtime validators, which, which are libraries that check types during execution to ensure that type safety is maintained. Let's touch on some advanced topics in type safety. Subtyping is an important concept. It allows you to use a subtype where a subtype is expected, enabling more flexibility while still maintaining type safety. For example, a method that accepts an object of type shape can also accept objects of type circle or rectangle if they intend from the if they inherit from the shape class. Polymorphism is another key concept that can affect type safety. It ensures that different types can be handled in a uniform way without breaking the type rules. Lastly, generics and type constraints in languages like Java and C# allow you to create flexible yet type-safe code by restricting the types that can be used with generics. To summarize, type safety is a crucial concept that ensures operations are performed on the compatible data types, preventing errors in your program. Compile time and runtime type checking each have their benefits, and type inference, annotations, and strict typing help ensure that type safety is maintained. By understanding and applying these principles, you can write more reliable and bug-free code. Welcome to day 9 of our programming course. Today we will be learning about control structures. We will cover sequence, selection, and iteration in programming, as well as conditional statements, loops, and recursion. First, let's talk about sequence. Sequence refers to the execution of instructions in a linear order, one after the other. Each line of code is executed in the order it appears, which is the most straightforward way of structuring a program. For example, when you assign values to variables, they are processed sequentially. Like in this example, int x equals to 5, b int b equals to 10, and int c equals to a plus b. This is a simple sequential flow. Next, we have selection. Selection allows your program to make decisions based on certain conditions. In programming, we use conditional statements to select the path of execution. The most common ones are if, else, and switch statements. For example, in the if-else structure, if a condition is true, one set of actions will be executed, otherwise a different set of actions takes place. Here we check if a number is greater than 0 using an if-else statement. If true, the program prints positive number, otherwise it prints non-positive number or negative number. Now let's look at iteration or loops. Iteration allows us to repeat a set of instructions until a certain condition is met. This is useful when we don't know the exact number of times an action needs to be performed. There are several types of loops in programming. The for loop is typically used when the number of iterations is known. The while loop checks the condition before every iteration. Finally, the do while loop ensures that the code is executed at least once before checking the condition. All of these help in repeating actions efficiently. Conditional statements are essential in controlling the flow of the program. These statements help us choose between different actions based on conditions. For example, the if-else structure allows us to check a condition and based on whether it's true or false, execute one of two possible code blocks. In this example, we are checking if a number is greater than 10. If true, we print greater than 10. Otherwise, we print less than or equal to 10. Now let's dive into recursion. Recursion occurs when a function calls itself to solve a smaller instance of the problem. Recursion consists of two parts, the pace case and the recursive cases. The pace case defines when the recursion should stop, and the recursive case calls the function again with a modified input. For example, in a factorial function, we keep calling the function with smaller numbers until we reach the base case, where n equals 0. So why is recursion important? Recursion simplifies complex problems by breaking them down into smaller, more manageable subproblems. It allows for elegant solutions, especially when dealing with problems like sorting, searching, or traversing hierarchical data structures like trees. For example, the Fibonacci sequence is a great example of recursion. By defining the problem in terms of smaller instance, we can calculate Fibonacci numbers efficiently. To recap what we have covered today, sequence refers to the execution of statements in a linear, step-by-step manner. Selection involves making decisions based on conditions using if, else, or switch statements. Iteration allows us to repeat code using loops like for, while, or do while. Recursion solves problems by calling functions within themselves, breaking problems into smaller parts. These control structures are the building blocks of any program, allowing us to write efficient and logical code. Welcome to Day 10, Variables and Memory Management. In this session, we will explore key concepts around variables, memory management, and the differences between stack and heap memory, as well as how memory allocation works in programming. To begin, let's understand what variables and memory are in programming. A variable is a named storage location in memory that holds a value. The type of data it holds is defined by its data type, such as an integer or a float. Memory, on the other hand, is where all your data and program instructions are stored while a program is running. Managing memory efficiently is critical for the performance and stability of software. Now let's look at stack memory. Stack memory is used for static memory allocation, meaning it's used to store local variables and function calls. Memory is allocated and deallocated automatically as functions are called and returned. It's fast to access, but it has a limited size. Once a function call completes its memory, it's cleared from the stack. Next, we have heap memory. Heap memory is used for dynamic memory allocation, which allows you to allocate memory for objects and large data structures during runtime. This memory is slower to access compared to stack memory, but it has a much larger size. Memory allocation on the heap persists even after a function call returns, unlike stack memory. To summarize the differences between stack and heap memory, stack memory is used for storing local variables and function calls with automatic memory management. If it offers fast access but limited size. Heap memory, on the other hand, is used for dynamic memory allocation, and while it's larger, it requires manual and or automatic management. The key difference is that stack memory is automatically managed, while heap memory requires more control from the programmer. There are two primary types of memory allocation: automatic and manual. Automatic memory allocation is managed by the compiler or runtime environment, such as with local variables and function calls. Manual memory allocation requires the programmer to explicitly allocate and deallocate memory, as seen in languages like C++ with functions such as malloc and free. Manual memory management provides more control but also adds complexity. Now let's talk about garbage collection versus manual memory management. Garbage collection is an automatic process in languages like Java and C Sharp where memory that is no longer in use is freed up automatically. While this simplifies the programmer's job, it can also add runtime overload. In contrast, manual memory management gives the programmer full control but requires careful tracking of memory usage to avoid memory leaks and errors. Memory management comes with its challenges. One common issue is memory leaks, which occur when memory is allocated but not properly deallocated, leading to wasted memory. Another issue is dangling pointers, which happen when a pointer still references a memory location that has been freed. Lastly, memory fragmentation can occur when memory is allocated and deallocated frequently in small chunks, making the available memory less efficient. So, how can we manage memory more effectively? For automatic memory management, consider using garbage collected languages when performance isn't the highest priority. For manual memory management, it's important to use memory profilers and tools to analyze memory usage. In languages like C++, smart pointers like std::, shared ptr can reduce memory management errors, and it's always important to regularly review your code to ensure memory is properly deallocated. To wrap up, we have covered key concepts of stack and heap memory, as well as the differences between automatic and manual memory management. Effective memory management is crucial for preventing errors like memory leaks and dangling pointers, ensuring that your programs run efficiently and without crashes. Both stack and heap memory serve different purposes, and understanding their differences will help you write better, more efficient code. That concludes today's session on variables and memory management. If you have any questions or need further clarification, feel free to ask now. I am happy to discuss any points in more details. Welcome to today's presentation on functions and procedures in programming. In this session, we will explore key concepts that help in writing modular and reusable code. A function is a block of code that performs a specific task and can be reused multiple times in a program. Functions help in breaking down complex problems into smaller, manageable parts. They allow us to write more readable, maintainable, and modular code. Here's how we define and call a function. To define a function, we specify its return type name, and the parameters it takes. For example, the function add takes two integers and returns their sum. When calling the function, we simply pass the required arguments like in add 3, 4 and get the result. In programming, we can pass arguments to the two functions in two primary ways, by value and by reference. When passing by value, a copy of the argument is made, so changes inside the function does not affect the original value. On the other hand, passing by reference allows the function to modify the original argument directly. Recursion is when a function calls itself in order to solve smaller subproblems. A recursive function has two parts, a base case which stops the recursion and the recursive case where the function calls itself. For example, a factorial function calls itself repeatedly until it reaches the base case. Recursion is important because it simplifies solving problems that have repetitive, self-similar patterns. Problems like sorting, searching, and traversing trees can often be solved more elegantly using with recursion. However, care must be taken with recursion as it can lead to performance issues like stack overflow if not managed properly. Closures are functions that remember the environment in which they were created, allowing them to access variables from their surrounding scope. High-order functions, on the other hand, are functions that take other functions as arguments or return functions as results. These concepts make your code more flexible and allow for advanced programming techniques. Functions can return different types of values such as integers, floats, or even objects. Function overloading allows us to define multiple functions with the same name but different parameter types. This helps in writing cleaner code when we have similar operations for different types of inputs. Lambda functions are anonymous functions typically written in a single line of code. They allow for concise and functional programming, often used as arguments for higher order functions. In Python, for example, a lambda function can quickly perform operations without requiring a full function definition. When it comes to function scopes, there are local and global scopes. Variables defined inside a function are local, meaning they are only accessible within that function. Global variables, however, can be accessed from anywhere in the program. Understanding scope and lifetime is essential for managing variable access and preventing errors. When solving problems, we often have the choice between recursion and iteration. Recursion can be elegant and simplify the solution for certain problems, but it may lead to issues like stack overflow. Iteration, on the other hand, can be more efficient for tasks that don't naturally fit into a recursive pattern. To summarize, functions allow us to modularize and reuse code. Recursion helps us solve problems by calling functions within themselves. Higher order functions and closures make our code more flexible and concise. Lastly, understanding scopes, return types, and function overloading are essential for writing efficient and maintainable code. Thank you for your attention. Now let's open the floor to any questions or discussions on the topics we have covered today. Feel free to ask about real-world applications of functions, recursion, or any other programming concepts. Hello and welcome to this presentation on Object-Oriented Programming or OOP. Today we will explore key OOP concepts including classes, objects, inheritance, polymorphism, and design principles that are essential for creating modular, maintainable, and efficient software. Object-oriented programming is a programming paradigm that revolves around objects. These objects contain data and methods that operate on that data. OOP promotes better organization of software and allows for easier maintenance and modification. The key benefits of OOP include abstraction, encapsulation, inheritance, and polymorphism. At the core of OOP are classes and objects. A class acts as a blueprint for creating objects which are instances of that class. For example, imagine a class car with attributes like brand and year, and a method start that defines how the car starts. Objects are the actual instances, like my car, that use these attributes and methods to perform operations. Inheritance is one of the key features of OOP. It allows one class to inherit properties and methods from another class, promoting code reuse. For instance, if you have a class electric car that inherits from the class car, the electric car will automatically have all the properties of car plus additional features like battery life and charge method. Polymorphism allows us to treat objects of different classes as objects of a common base class. This is achieved through method overloading and overriding. Overloading happens at compile time, while overriding occurs at runtime. For example, in method overloading, we can have multiple methods with the same name but different parameters. In method overriding, a subclass provides a specific implementation of a method defined in a superclass. Let's now look at the four fundamental principles of OOP: abstraction, encapsulation, inheritance, and polymorphism. Abstraction hides the complex implementation details and shows only the essential features, while encapsulation bundles data and methods, protecting the object's internal state. These principles work together to make software easier to understand and maintain. Design patterns are proven solutions to common problems in software design. They offer best practices for solving recurring issues and improving software flexibility and maintainability. Some popular design patterns include the singleton, factory, and observer patterns. These patterns can help make our software more modular and acceptable to changes. SOLID is an acronym for 5 principles that guide object-oriented design. These principles, single responsibility, open-closed, Leskov substitution, interface segregation, and dependency inversion, ensure that software is easier to maintain, test, and scale. By adhering to solid principles, we can build software that is both efficient and robust. Let's consider a real-world example of inheritance and polymorphism. We can create a class vehicle with a move method. Then we define two subclasses, car and bike, that each override the move method to provide specific functionality. This demonstrates how polymorphism allows us to treat different types of vehicles as a common vehicle object while each performs its own action. In summary, object-oriented programming helps us break down complex systems into manageable parts. By using key concepts like classes, inheritance, polymorphism, and principles like SOLID, we can create software that is modular, scalable, and easy to maintain. Design patterns further help in solving common design issues, improving code quality and flexibility. Thank you for your attention. Now I will be happy to take any questions you might have Feel free to ask about any aspect of object-oriented programming, whether it's about specific concepts, examples, or how to apply these principles in real-world projects. Welcome to this presentation on functional programming concepts. In this session, we will explore key ideas such as immutability, pure functions, higher order functions, and more. Let's dive into the core concepts of functional programming. Functional programming focuses on several key concepts. First, immutability means that once a value is assigned to a variable, it cannot be changed. Second, pure functions are those that always return the same output for the same input with no side effects. Next, we have higher order functions, which takes other functions as arguments or return them as results. And finally, referential transparency, which allows us to replace an expression with its value without changing the program's behavior. Immutability is a cornerstone of functional programming. Once a variable is assigned a value, it cannot be modified. This reduces side effects, making the code easier to reason about. Immutability also enhances concurrency safety, as there are no shared mutable states that can lead to unexpected results. Next, we will discuss pure functions. A pure function's output depends solely on its input values with no side effects. This makes pure functions highly predictable, easier to test and debug. An example of a pure function is a simple addition function, where the result is always determined by the inputs and no external states are modified. Functional programming treats functions as first-class citizens. This means that they can be assigned to variables, passed as arguments, and returned as results. Higher order functions are a key feature as they take other functions as inputs or return them as outputs. For example, the map function can apply a given operation to each element in a list. Lambda expressions are anonymous functions defined inline. These allow us to define small functions on the fly, making code concise and readable. For instance, a lambda expression is in Haskell can be used to multiply every element of a list by 2, simplifying the operation. Lazy evaluation is a strategy where expressions are only evaluated when their values are needed. They can lead to significant performance gains, especially in large data sets. It also allows us to work with infinite data structures, where the elements are computed only when required. In functional programming, recursion replaces loops as the primary way to iterate. Recursive functions call themselves with modified parameters to solve a problem. For example, calculating the factorial of a number can be done through recursion, where the function calls itself with a reduced values. Here's an example of recursion in Haskell. This function SumList recursively sums the elements of a list by adding the first element to the sum of the rest of the list. The base case is an empty list where the sum is 0. Libs is another language known for functional programming. In libs, we can define functions like the factorial function using recursion. This highlights lib's powerful support for symbolic computation and functional programming. Let's compare functional programming to imperative programming. In functional programming, we focus on what we want to compute, while in imperative programming, we focus on how to perform the computation. Functional programming avoids mutable state and side effects, whereas imperative programming typically uses loops and changes states. Functional programming offers several key benefits. Modularity, since functions can be reused throughout the program. Predictability, as pure functions are easy to test. And concurrency, since immutability always allows for safer multi-threaded programming. However, functional programming also comes with challenges. There's a learning curve when transition from imperative to functional programming. Recursion and immutability can introduce performance overhead, and functional programming languages have more limited adoption in some industries. To conclude, functional programming emphasizes immutability, pure functions, and higher order functions, offering benefits like modularity, predictability, and concurrency safety. However, it may also present challenges such as performance and learning curve. That wraps up the presentation. If you have any questions, feel free to ask now. I would be happy to clarify any concepts. Welcome to day 14, Logical Programming. In this session, we will explore the key concepts and applications of logic programming, a declarative programming paradigm based on formal logic. Let's dive into this fascinating topic. Logic programming is a programming paradigm where we express facts and rules about a problem domain, and the system reduces answers through logical inference. Unlike imperative programming, where we focus on how to do something, logic programming is about what to do. It allows us to describe problems in a more natural, declarative way. Let's explore the key concepts in logic programming. First, we have facts, which are basic statements about the world. For example, John loves Mary. Next, we have rules, which allow us to infer new facts from existing ones. An example of a rule could be, if John loves someone and that person loves Mary, then John loves that person. Finally, we have queries, which are how we ask the system to deduce solutions or verify facts. Prolog is one of the most widely used languages for logic programming. In Prolog, facts are written as simple statements like loves John, Mary. Rules are defined with a head and a body, and queries ask the system whether something is true. For example, we can ask Prolog, does John love Mary? And Prolog will check the facts to answer. Rule-based systems are a core component of logic programming. These systems make decisions based on a set of rules which follow an if-then structure. For example, in a medical expert system, a rule might state if a person is sick and has fever, they should see a doctor. Rule-based systems are used in applications such as expert systems and decision support systems. One of the fundamental techniques in logic programming is backtracking. This technique helps the system explore multiple possibilities to find a solution. If one possibility fails, the system backtracks and tries another path. For instance, when Prolog tries to answer a query, it may need to backtrack to explore all possible solutions. Unification is another key concept in logic programming. It is the process of making two terms identical by finding a suitable substitution for variables. For example, in the fact loves John, X, prologue will attempt to unify X with Mary if the fact loves John, Mary exists in the knowledge base. Unification is what allows prologue to match facts and rules to provide answers. Let's look at an example in prologue. Consider the following facts: Father Abraham, Isaac, Father Abraham, Isaac, Jacob, and Father Jacob, Joseph. We have a rule for grandfather grandfather X, Y, Father X, Z, Father Z, Y. When we ask prologue grandfather Abraham, X, it uses backtracking and unification to find all possible solutions. Prologue will deduce that Abraham is a grandfather to both Jacob and Joseph. Logic programming is widely used in various fields. In expert systems, it helps simulate human expertise by encoding knowledge in rules. In natural language processing (NLP), logic programming can be used to represent the syntactic structure of sentences. It also employed in artificial intelligence, where reasoning and decision making are central, as well as in constraint logic programming, which solves complex problems like scheduling and optimization. To summarize, logic programming is a powerful paradigm focused on formal logic and deduction. Prolog is a popular language used for this purpose, with its reliance on facts, rules, queries, backtracking, and unification. This paradigm has many applications, including expert systems, NLP, and AI, and it provides a unique way to solve problems. That concludes our overview of logic programming. Do you have any questions or comments? Let's open the floor for discussion.